Mm. Yeah, welcome to our webinar. My name is Ivan Svetenkov. I am a lecturer of Marketing Analytics at Lancaster University and Director of Lancaster Center for Marketing Analytics and Forecasting. And today I will be your chair, and I will be chairing a talk by Stefan Kolassa. Stefan Kolassa is lead data scientist. I always struggle to correctly name you. I know that data scientist is there, but I'm not sure.
My official title is data science expert.
Data science
so people
expert.
know that I know what I'm doing.
Okay, so Stefan is data science expert in SAP, and he's one of the best experts on retail forecasting and lots of other great things like intermittent demand forecasting. And today he will be talking about probabilistic forecast evaluation. So how will this talk happen is that first Stefan will talk, and then we will accept some questions. So if you have questions, you can type them in the chat, or when we accept questions, you can raise your hand and we will let you ask Stefan directly. I think that's it from me. Yes, and this video is also recorded and it will be uploaded to the channel of Tufts. Okay, Tufts nonprofit organization. So keep in mind that if you unmute yourself and show yourself, that you will be recorded and uploaded on YouTube. And if you're watching this on YouTube, don't forget to like this video and to subscribe to the channel. That's it from me. Stefan, over to you.
All right, thank you. Thank you, Ivan, for chairing me. Thank you, Jesus, for having me here. And thank you, everybody, for attending this talk. Let's try and keep you interested until the very end. Let's talk about probabilistic forecast evaluation. So we have a long evening ahead of us. We're going to talk about what are probabilistic forecasts and why should we care. We're going to talk about evaluating quantal forecasts, interval forecasts, predictive densities. We're going to talk a little about scaling for comparability, and after that, those are all the good news. And now we're going to talk about the not quite so good news about the pitfalls that you might fall into of accuracy estimation. We're going to talk about go beyond accuracy for a slide or two, and then we'll conclude at the end. All right, lots of things to do. Let's start. What are probabilistic forecasts and why should we care? All right, so what are probabilistic forecasts? There's really no hard and fast definition of a probabilistic forecast. So probably it's not the stuff that you do when you do expectation forecasting. So if you just say my expectation forecast for tomorrow is we will have 9 inches of snow, probably not, and that's probably not probabilistic. But quantal forecasts, like there's a 90% of rain tomorrow, or our demand is has a 95% quantal forecast of 10 units, that's probably going to be probabilistic. We might have interval forecasts or prediction intervals. So we have a 90% prediction interval between 2 and 10 units being sold tomorrow. Density forecasts that we're going to talk about, those are probably all probabilistic forecasts. So I'm just going to work with the definition of forecasts that explicitly acknowledge uncertainty in some way. So here's a little example, and this is an example that's going to accompany us for the entire talk. So expect to be seeing that for quite often by now. This is just a simulated time series. I've just simulated something, and these are just IID data, independent and identically distributed realizations. So there's really nothing time series-y in this really at all. These are log normal. Sorry. Okay, got my PowerPoint back on control here. So this is just log normal with log mean 1, log variance 1. So we know everything about this. This is a historical time series in black. So this is something that we might have seen. And after time point 100, we might go into forecast. And I put in this pale yellow, this is the density, the actual density, the log normal density that I used to generate these data. And I just put that on the side because it's more natural because the vertical axis is what we actually observed. So this is the true density that we generated these data from. And since we're assuming that this is also future density, this is a correct density forecast. I'll also have 3 different lines in here. And those are the point forecasts. And since there's no dynamics in here, the point forecasts are flat lines. Those are the point forecasts that you'd output if you wanted to optimize or to minimize the expected absolute percentage error, or the expected absolute error, or the expected squared error. And if you're surprised that you get 3 different forecasts depending on which error measure you want to minimize, then you may want to go to this link at cross-validated down here, which goes into this. But that's not the topic for today. Today, the topic is probabilistic forecasting. So how should we care, or why should we care about probabilistic forecasting? What's the point? Well, the point is really that forecasts are not ends in themselves. And forecasts are sometimes a little shocked when I say that, but few people forecast for the forecast's sake. We always use the forecast for some kind of decision, business decision, typically later on. So for instance, we might want to do capacity planning. We want to stock up the shelves so that we have stock on hand when people come in and want to buy something. We might want to plan for the capacity of a call center, which involves forecasting how many calls are we going to get in the next couple of days, weeks, months, per 15-minute increment, for instance. And for any kind of capacity planning, safety stock setting, we need to take the variability into account, because the expectation forecast only tells not even half the story, much less than half the story. So here's 3 different, again, simulation data sets on the right-hand side. They all have the same expectation. They're, again, I believe, log normal, don't ask me. But the point is, even if they have the same expectation of what have you, it could be 1 or something, we see that they're hugely different variable. Like you see that the top one has sales that go, or movements, or whatever it is, observations going up to 55 or 60, lots of them above 10. And the middle and the bottom one, they're much less nervous. And the bottom one never goes above whatever that is, 15 or something like that. So if we want to have an order up to a level, or a safety amount, a safety stock, a safety capacity that allows us to reach a service level, a target service level of 90%, what have you, then we'll need a lot more safety stock at the top situation than at the bottom situation. So understanding not only the central movements and the central tendencies of our future process that we're in forecast, but also understanding the higher movements, or the higher quantals, is crucial for any kind of subsequent business decision. Because if you just deal with the first moment, just deal with the expectation, not with the higher moments, then you're going to run into problems when variability strikes, and variability always strikes. So what we really need is quantal forecasts for safety stocks, or if our safety stock calculation is not completely aligned with the time bucket that we're forecasting in, then we'll need to do some kind of convolutions and look at quantals of sums of random variables. And for that, we really need full predictive densities and covariances and lots of very complicated stuff. So that's why we should care about probabilistic forecasts. All right, let's talk about how to evaluate these kinds of probabilistic forecasts. And as we saw on the first slide, there's different kinds of probabilistic forecasts. There's quantals, interval forecasts, predictive densities. So we're going to look at all of these in turn. Starting with quantal forecasts. What is a quantal forecast? A correct quantal forecast is for a certain pre-specified level, which I'm going to call alpha, between 0 and 1, like 9%. That's 0.9, alpha equals 0.9. That's a number, q hat, such that the probability that our future realization, y, is less than or equal to q hat is exactly alpha. So we want to have a number. For instance, here's one of our example. That's the example we saw at the very beginning. And we see 2 correct quantal forecasts, one for a 90% quantal, one for an 80% quantal. So depending on what target service level we want to set, if we want to have a service level or an in-stock probability of 0.8, then we want to stock up to 6.31. If we want to have an in-stock probability of 90%, then we want to stock up to 9.79. So, and that already shows us that often we want to calculate multiple such quantal forecasts, one for each different level of alpha. All right, so how do we assess whether a given quantal forecast is any good? Well, we can always say, well, this is supposed to be a level such that we have a pre-specified probability of not exceeding that level. So we can just evaluate the time series moving forward and count how often the time series, the actual process that we're forecasting, how often that is above or below that quantal forecast. And obviously, we should be having a proportion of alpha of observations that are below or at most that quantal forecast. So you can just count, well, how often do we exceed this quantal forecast? And is that a proportion of roughly alpha? And then we can perhaps run a binomial test or something, and that tells us, well, where our actual coverage exceeds this value or is below this value by a statistically significant amount. But this is discontinuous in the yi and is really not very, very helpful as such, because yeah, it requires a lot of data and it's not very helpful. What's more common or more useful is a pinball loss. And there's this rather cryptic number here, this cryptic function that takes our quantile forecast and an actual realization, y, and then, well, if the quantile is less than, if the quantile forecast is less than the actual, then the actual exceeds the quantile forecast, then we penalize that by alpha times the discrepancy, by the exceedance between the quantile and forecast and the actual. And if the actual is below the quantile, then we penalize that by 1 minus alpha times the discrepancy. And this is rather cryptic. And why is this useful? It is useful because this one is minimized, this error is minimized in expectation by the correct quantile. So if we minimize this, then we reach a correct quantile forecast. So that's the pre-specified coverage. This number, or this formula, this loss, this pinball loss, was probably not invented. I have no idea who came up with this first, but it was popularized by Roger Koenke in the context of quantile regression. He has this eponymous textbook, Quantile Regression, very useful, very, very helpful. He didn't use it in the time series context at the beginning, but it's completely useful for time series. So here's another plot of this, just to get an idea of what's happening here. So if we have a pre-specified value of alpha of 0.8, then we can use some kind of forecast and say, okay, if the actual is 10, then the pinball loss is minimized, of course, if we forecast this 10 here. But if the actual is, if the forecast is 15, then this is the loss that we incur for an actual of 10. And if the actual is 0, then the loss is something up here. And this angular shape is what motivated this term of pinball loss, because, well, there's two ways of looking at it. Either it's the way that a ball coming in is deflected out at a different angle, or you could say it's perhaps the two paddles of a pinball machine. Either one I've heard. All right, but there's also a different way of looking at things here. And that's this number down here. So we have our time series, which is this one up here. And so we just simulate tons of data points like this here. And we say we have a quantile forecast, which is perhaps the 6.31. That is actually the correct quantile forecast. This is here. And we say, what's the expected loss under this quantile forecast for an alpha level of 0.8? And then we can also look at the loss for different quantile forecasts. So if we say, well, our quantile forecast is 15, then we see that the expected loss is much larger. And this illustrates that the minimum of the expected loss is at the correct quantile forecast. And this is why we want to use the quantile forecast, because it pulls us towards getting the correct quantile forecast. This is how you forecast, or how you evaluate quantile forecasts. A couple of pieces of literature down here for further reading. All right, now we have quantile forecasts. We can also look at interval forecasts. Interval forecasts are really two quantile forecasts, a higher one and a lower one. And there's actually multiple different interval forecasts. There's a standard one. That's the one that people usually think of. That's a central or equal tail prediction interval. And that just looks at the higher and the lower quantile forecast so that there is an equal amount of probability mass at the top and at the bottom. And actually, it's easier to see that if you look at a central 0.8 or 80% prediction interval, and that just takes a 10% quantile forecast and a 90% quantile forecast and says everything between these two, that's my prediction interval, because I have a 80%, I hope to have an 80% chance of being in this range, in this interval, and there's a 10% chance that I'm above it and a 10% chance I'm below it. So there's symmetry in here. We can, for instance, for our example here, again, the same example, and the quantile forecast, the interval forecast here, prediction interval would be this number here. We have an 80% chance of falling between these two numbers, between 0.75 and 9.79. And there's a 10% chance of being up here above the 9.79, and there's a 10% chance of being below the 0.75. Okay, now given any prediction interval, how can we assess this, whether it's any good? This is assessed typically by using the interval score or the Winkler score, because Winkler, of course, wrote the paper in 1972. And this is a function that takes a prediction interval, a lower and upper limit, and an actual. And that has actually two terms. The first term is a sharpness, and that is just the length of the interval, the width of the interval. And the second term is a calibration term, and that essentially looks at, are we within the interval or are we outside the interval? And that one, so the first term penalizes it if we have an interval that is too large, and the second term is penalized if we have an interval that does not cover the realizations. And the smart thing, the good thing about this is that this is a consistent scoring function. That is, it is minimized in expectation by having a correct central prediction interval. And again, papers at the bottom that go into the gory details. However, a little detail on the side is that there is also other prediction intervals, because there's other intervals that might have an 80% coverage that are not a 10% and a 90% quantile forecast, but something else. For instance, you could also require having the shortest prediction interval that covers 80% of the actuals. So at the right-hand side, we see, again, our little example where we know everything, so we actually know what the correct prediction intervals are. And here's the central prediction interval. That's what we just saw in the last slide. And then we have a shortest 80% or 0.8 prediction interval. And we see that this goes down to 0.18 and goes up to 6.44. That still has 80% coverage. It's just that it's not a 10% and a 90% quantile forecast anymore, but it still has 80% coverage, and it's the shortest such interval. The bad news is that this is in general not elicitable. In general, there is no loss function that will lead us towards this interval, right? Again, papers down here. Alternatively, you might not want to specify the coverage, but you might want to specify the length of your prediction interval. Like you might want to say, I want to have a 7.5 length prediction interval that has the highest possible coverage. That's another possible way of specifying a prediction interval. And in this case, I just used a length of 7.5, and the highest coverage prediction interval of this length is just the one between 0.09 and 0.59. And that actually has a coverage of 84%. That's another way of asking for a prediction interval, and that is actually elicitable by having a 0-1 loss. So just have this interval and then count how often your future realizations fall within the interval or outside the interval. And if you minimize this number of realizations that fall within the interval, then you'll be driven towards having this highest coverage prediction intervals. You might also want to have a predictive highest density region, which is a even more exotic prediction interval, and that's not elicitable in general, even for densities that are unimodal, like actually multimodal densities. And then this highest density region is not even an interval anymore. It might also have highest density intervals, which is yet another thing. And again, these are not elicitable, and they're really not that important in practice, because in practice, everybody, when they think about a prediction interval, everybody is thinking about a symmetric or equal-tailed prediction interval, so the one that we just looked at on the previous slide. All right, now we've looked at quantile forecasts, we've looked at interval forecasts. Now let's talk about predictive densities. Well, what's a predictive density? Actually, if you look back at always the same, it's always our little example here. We have our time series here, that's what we saw, and now I want to forecast what is a predictive density. A predictive density is really exactly what we see here. A predictive density is a density function, or alternatively a cumulative density function, so a probability density that we believe corresponds to future realization. So it really encapsulates everything that we know about one future realization. We might even look at multidimensional predictive densities that encompass or encapsulate also the covariances between future realizations, and that's something that very few people are actually looking at. So let's just look at marginal densities, so densities for every single future time point at a time. In this case, since we've simulated this time series and we know that it's log normal 1, 1, we know that the correct density is this one here. Of course, in a real situation, we haven't simulated our data. We need to look at past data, past observations, and we need to calculate this density, and we need to output this density, and then in some way assess whether this density is any good. And the key thing here, the key tool for this is scoring rules. So a scoring rule, that's a mapping that takes a predictive density, f hat for instance, and a single realization to the reals. And this is what we call a scoring rule. Now, in general, scoring rules are boring. Interesting scoring rules are proper scoring rules. Those are the ones, those are scoring rules that are minimized in expectation if we take the expectation over the y by the true density, so that if we forecasted correct future density then and evaluate it, then we expect a lower score than for any other scoring, and then for any other predictive density, or at least not lower than for any other predictive density, but at most the one that the true future density has. We could also have a strictly proper scoring rule, which is minimized only by the true density. So this is a slightly more stringent criterion. In this case, for a proper scoring rule, it's enough to have a predictive density that achieves the minimum. It might not be the true future density, it might be some other density, but if they have the same expected score, then this is proper. And in this case, we're really led to the only solution to the actual true density, and it's the only one that minimizes this proper scoring rule. And very often, strictly proper scoring rules only exist relative to certain classes of future densities. If you just allow any density, then very often you'll not get any better than having proper scoring rules. Important detail, this is a detail that is actually important. There is also the opposite convention, because here we are talking about minimizing everything. We want to have low scoring rules, we have low scores, we have losses, we want to minimize everything. But there's also people out there in the literature that want to maximize everything and want to have high scores. So just be careful. Of course, mathematically, it's just a question of putting a minus sign in front of the score. And so either having it or not having it, it doesn't really make a difference in terms of the mathematics. It's just you need to interpret, is lower better or is higher better. But I think it's a little more common to have scores that are losses. So we want to minimize the scores. So that's a convention that I'm going to work with. Just keep that in mind. And whenever you see a scoring rule, understand which convention is being used. Examples. So there's a couple of examples of scoring rules that are out there that are more or less common. So just consider some predictive density f hat, and we have that of course gives rise to a predictive cumulative density, which we're just going to call capital F hat, and we have an observation y. All right, so here's a zoo of proper scoring rules, and I think they're all proper, not strictly proper in general. Don't quote me on that, but that actually underscores why I at least don't think this distinction between properness and strict properness is very useful. I really don't care. All right, the first candidate is the log score, which just says, okay, given a predictive density f hat and the realization y, just evaluate the predictive density at the realization, take the log, and take the minus sign in front of that. And this is just the log likelihood or the negative log likelihood. And this is actually where we want to minimize. We want to maximize the likelihood or the log likelihood. So we want to minimize the negative log likelihood. So this comes very naturally to statisticians or statistical data scientists because, well, it's just the log likelihood, right? So we want to maximize that. put a minus sign in front of that, minimize that, and voila, you have a proper scoring rule and you can assess your predictive distribution. There is also another very common one, that's a continuous ranked probability score. And what is this here? Well, here we have the cumulative distribution function. And what this does is really, it's just the L2 norm of the difference between our predictive cumulative distribution function and the actual cumulative distribution function. It's just, I'll take the integral over the square, that's just the L squared norm. The continuous here, the C here, hints that there is also a non-continuous form of this. So there's also a ranked probability score where you just have not an integral, but a sum over possibly finitely or infinitely many realizations. And so there is an alternative of that for non-continuous realizations. There's other things like the quadratic score or the Bria score, which is just evaluate the predictive density, take -2 of that, and plus add a correction term essentially, which we're going to come in 3 lines. There is a spherical score, which is very similar. Evaluate the predictive density and divide it by a normalization term. And this term is just the 2 norm of the predictive density, right? So just take the predictive density and square integrate that from -infinity to infinity. Now we have multiple different scoring rules, proper scoring rules. We could be using any of those. And happily enough, there's one paper that is very useful here. That's Merkel and Stavers, full details down here. And they actually point out that there is only a small number of families of proper scoring rules. And most of these are just special cases of these proper scoring rules. The ones that are used most commonly in practice are the log score and the CRPS. Here's one detail, one thing here. The CRPS really, well, if you look at the log score, this is local in the sense that it only cares about the value of your predictive density at the actual outcome, at the outcome that you actually observed. So if you, as long as you keep that fixed, you can whittle around and shuffle around all the other predictive probability mass as you want, and it's not going to change the log score. The log score, it doesn't care at all. It's just the point of being proper is only that if you minimize it, then in expectation, you'll get to the correct predictive density, which is the true density. But it's not very helpful because it's local. Anything for limited samples or finite samples, you could be shuffling around your probability mass as much as you want, as long as you keep the part constant where you actually saw the observations, and that is a bit hard to swallow. Whereas the continuous ranked probability score, that one actually will penalize it if you move probability mass away from the realizations that you saw, because then you'll be having a high value of this number that you're integrating if you're moving lots of probability mass to the extremes or to somewhere else. So the CRPS in that sense is not local. It does not only care about your predictive density at the point that you actually observed. It also cares about everything that's somewhere far away. And that's probably why the CRPS is, in my observation, a little more commonly used, at least in academic forecasting. Quadratic or spherical score are really much less used, although the Bria score, that's actually very commonly used, not in forecasting, so in numerical target forecasting, but in classification. If you run classification, so you just have 2 classes or multiple ordinal class, not ordinal, but cardinal, categorical classes, or you want to forecast, you want to predict whether something is red, green, yellow, you don't have an order on that. That's something where the Bria score, or again, the log score, is very useful. But in numerical forecasting, where you have continuous or at least ordinal outcomes, that's where the Bria score is not really used that much. One more point as to why to use one rather than another proper scoring rule is, let's look at the log score again, because it's still being used. One thing that is important about this here is if you see an outcome that your predictive density assigned a 0 probability to, if you see something that you believe was impossible, right? So you might be, perhaps you're deriving your predictive density from some kind of resampling approach or Markov chain Monte Carlo approach, where you're simulating from something and then you're looking at the empirical density function of those simulations. Then often enough you might not see any realizations on some points of the possible spaces. So you might have a forecast, a predictive density that is 0 over at some places, and then you might actually see something that is impossible by what you just thought. Well, what's going to happen here is that the f hat of y is going to be 0, and then you're taking the logarithm of 0, and your computer is going to be very unhappy at you, right? Because the logarithm of 0 is undefined, and you'll get either an infinite somewhere or an NA or something else, and it's just going to be very unhappy. Now, some people could, and actually, looking at the other ones here, at the other scores, those don't have this feature, this property. Let's call it the property, because is this a bug or is this a feature of the log score? And actually, I have another thread on cross-validated on which scoring function to use, proper score to reuse, log or Brier score, more in the context of classification than in forecasting. And so there's different things in this differentiation between the log and the Brier score. And one of those things is exactly this point here. What happens if something happens that we believe was impossible? The log score explodes. The Brier score, or all of the others here, give you a number that is not infinite. And so we have to think about, is this a bug or is this a feature? I personally like this feature. I think it's a feature, it's not a bug, because if you see something that you believe should be impossible, then you should really, this should jump out at you. It should, because then something is fundamentally off. If you're not even considering the possibility of some certain outcome, and the outcome is indeed possible, then you should be notified in a way that is hard to ignore. And that is why I personally do like the log score. All right, scaling for comparability. So we've had lots of error measures for quantal interval density forecasts, but typically we don't want to forecast a single time series. So we might want to forecast the sales of many products or demand for many things or many other things at the same time. And those may be on very different scales. So if you're forecasting, I know a little about retail forecasting. If we're forecasting milk sales at the supermarket, that moves much faster than spices, for instance. So, and you'll get completely different errors for your forecast for spices and for milk. But you may want to have the errors or the accuracy of the scores to be comparable. So it makes sense to at least in some way make these comparable so we can compare them. There's two main approaches here, really. And one of them is take your score or your loss or your error, whatever it is, and just scale it by the score or loss or error that is achieved by a benchmark. So we might want to, for instance, use as a benchmark the past historical average as a point forecast, or when you're forecasting in probabilistic sense, and the empirical cumulative distribution function of past sales or past demands or past observations. That is a density forecast. That is a very simple and probably the easiest density forecast, and we should definitely be able to beat that. Often enough, we are not. And so we can take the empirical cumulative density function of past observations as a density forecast. We can evaluate this using our proper scoring rule, log score, CRPS, what have you. And that is like a benchmark for the score that our actual forecast should improve on. So typically have a lower score. So we could just take the score that we achieved with our focal time series forecasting algorithm and divide it by the score achieved by a benchmark. And that is very similar to the mean absolute scaled error, where we scale the mean absolute error by the error achieved in sample by the naive one-step ahead forecast. So that's the same idea. The second main approach is to take the score and scale it based on the average level of time series. That's even simpler because we just have to calculate the mean, and then we hope that the score will scale linearly with the mean of the time series. That is very much related to this weighted MAPE, which is just the mean absolute error divided by the mean of the forecast. One example where that was used is in the M5 forecasting competition in the uncertainty track, where they requested quantal forecasts. So 9 different quantal forecasts. And so what they used to assess this, because they had 30,000 different time series of very different levels, is they took the pinball loss, which was a good thing, and they scaled that by, I believe, the mean of the series. I actually don't even know, or by the pinball loss used by some benchmark method. So it was one of these two approaches. And there's the paper, and anybody who's interested can find out what exactly they did. All right, so now those were the good things, and now let's look at the things to be careful of, the pitfalls of accuracy estimation. All right, so here's one pitfall or one thing to just keep in the back of your head. So things like consistency of the Winkler score or properness of the CRPS, those are properties of expectations of scores if our forecast is correct. So if we have a correct density forecast, then we'll have a minimum score if the score is proper. In practice, we don't have the actual density of the process that we're forecasting, because if we had that, then we wouldn't be forecasting in the first place, right? So what we have is we have a set of future realizations, and we have a set of future densities or interval forecasts or quantal forecasts, what have you. Usually our forecasts will not be, our density forecasts will not be the same going forward at every point in time or for every time series that we have. So typically we're not even having the identical distributed part, and I'm not even talking about the independent part here. And so we may be estimating the score by just taking the average score over n outcomes for one density forecast for each time point I, for instance, or each time series I, and its associated realization yi, and comparing that with the same average score for a different density forecast. And well, this formula looks quite different from that one up here, right? What does this tell us? So if one of these achieves a lower average score on some test set than another density forecast, what does that really tell us? Well, it's consistent with one of these density forecasts to be closer to the true distribution, but is this evidence? And this very much ties into what are p-values really, but let's not go down this rabbit hole. A simulation. I don't like thinking, and computers are cheap, so I always like to simulate. So let's just assume that we simulate that we have 100 log normal 1-1 actuals, and you've seen that before by now. This is always our example that we've been using here. So we simulate 100 actuals. So we assume that we have 100 data points to evaluate our forecasts on. And now suppose that we have 3 competing density forecasts. So candidate 1 is the log normal 1-1. So that's the actual one. That's the true one. That's the one that we want to find, right? So log normal 1-1. That's the density that we simulated our data from. But we might also have misconceptions. For instance, we might have somebody might say, no, these data come from a log normal 1/4 5/2, and the other one, no, it comes from a 5/4 1/2 log normal. And why did I choose these weird numbers? Well, it's because these 3 densities, these 3 predictive densities, all have the same mean. So the expectation forecasts for all 3 are identical and are all correct. So they all have the same expectation forecast. But of course, if we set safety amounts based on either one of these, then we'll have very different target stocks or target capacities than if we use the correct one. All right, so we can calculate the log scores against all these 3 candidates, and then just redo this entire exercise 500 times. So we get 500 log scores for the N11, we get 500 log scores for the 1/4 5/2, and 500 log scores for the 5/4 1/2. And then we get a plot like this here, where we plot all of these. And what do we see? Well, the horizontal bars here give us the mean, and as we see the mean, the estimate of the expected log score is lowest for the correct predictive density, second lowest for this one, third lowest for this one here. So it's up here. So everything is correct. The correct density gives us the correct score, the correct log score on average. And if we just look at every single data point and every single one of these 500 simulations, and we see that in 66% of cases, the log score tells us that the log normal, the correct density, has the lowest score. And in about 33% of cases, we see that this second one has the lowest score. And in about 1% of cases, 1% of cases, we see that this one has the lowest score. So, and in our situation of actually running forecasts, we just see one of these. We see a triplet of points, and so chances that that the one that we are looking for, the correct density, has the lowest score is just 66% in this particular case. In other cases, we might not even have the correct score and the correct density among our candidates. We might just have different ones that are differently wrong. So honestly, this is one reason why I personally am not overly impressed by minor accuracy improvements, because accuracies, scores, losses are all estimates based on more or fewer data points. And of course, we can also overfit on these scores. So just saying, well, let's do this very often. Well, if we don't get more and more data, test data, then we might as well overfit on these data points. Beyond accuracy. So provocative title here, does accuracy even matter? We are forecasters, and of course we fetishize accuracy, but take an example as this thing here. So here's a time series. Now actually one of the M5 time series, so retail sales at Walmart over 3 years of data. And what am I going to do with that? I'm actually going to run another simulation. So I'm simulating different aggregate quantal forecasts for this particular time series here by resampling. So I'm just getting some variability in my quantal forecasts. And then I'm simulating using these quantal forecasts as an order up to level. So I'm just simulating supermarket replenishment. I'm saying, okay, let's simulate one reasonable quantal forecast for this thing here and say this is a 90% quantal forecast. I'm going to fill up to this level and hope to achieve a 90% service level using different pack sizes, because sometimes you can only replenish in singletons. You can put in single units, lawnmowers. Perhaps you can only replenish in pack sizes of 2 or of 4 or of 8, because you cannot just put in a single bottle of shampoo. You always put in a full pack of 8 bottles of shampoos. So we record the pinball losses, which is what we've just been talking about, and we record the achieved service level. And then we want to see, okay, how do the pinball losses of different forecasts and the achieved service levels, how do these hang together? Here's a little plot where I have lots of points for the different simulations. I have lots of pinball losses, lower is better, right? And we have the achieved service level. And the red line here, that's the target service level of 90%. We wanted to achieve a 90% service level. That's why we calculated these 90% quantal losses for our 90% quantal forecasts, and we assessed them using 90% pinball losses. And then the black line, that's just a regression line. And so we see that if the pack size is 1, then there is a clear relationship, right? Lower losses, so in those simulated quantal forecasts that had lower losses led to higher service levels. And if you had a higher loss, then you had lower service levels. If the pack size is 2, then this relationship gets weaker because this regression line between the two numbers gets flatter or more horizontal. And if the pack size is 4, then this regression line gets flatter even. And the other point to see here is that if the pack size is 2 or the pack size is 4, then any quantal forecast, every single one, leads to an achieved service level above these 90% that we wanted to achieve, right? The point of the forecast was achieving a service level of 90% or more. And so we did smart things and calculated different quantal forecasts and evaluated them using the correct loss, which is the pinball loss. And in the end, sorry to say, but it didn't matter. Because if we can only replenish in pack sizes of 2 or in pack sizes of 4, then any replenishment, essentially just replenish whenever you're below some number and you're good. You don't need to do any forecasting, and the quality of the forecast does not matter in a business sense at the end. And of course, this is just one simulation, and it hugely depends on the logistical parameters and how often you replenish and what your, how large or what the scale of your time series is, all kinds of things. But this is just to underscore that accuracy is not an end in itself. what we're forecasting for and what accuracy is important for is business value. If we can drive business value using forecasts, then that's good. And if we're not driving business value, then forecasting is just kind of something for us nerds to amuse ourselves. And let's not tell those people that pay our salaries that we're not driving any business value here. Because there's other things to forecasting, to quality than accuracy. On the one hand, there is accuracy and there's business value. These two are very much related, of course, but there's also other things. I like to point out that there's data requirements. If you have two different forecasting methods and one requires much more data than the other, then there's a question: does higher accuracy of the more data hungry one drive more business value, or is this just using up resources for no gain? And there's actually other resource requirements, and one of them is the time of highly paid data science experts or people that actually know how to deal with this stuff. Our time is not limited, we're expensive. And if you run a forecasting method that does not generate value, but that costs expertise or costs other resources like storage space, computing powers, AWS cycles, even electricity, stuff like that, then you're probably doing something wrong. There is understandability and explainability, and closely related maintainability and debuggability, which I think is terms that I personally coined. Well, I think it's clear what's meant here. There might be a more complicated method that might be more accurate and might be driving more value as such. But if it's hard to understand and hard to debug when things go wrong, then that might dominate the value driven by the higher accuracy. So there's a trade-off, and it's something to keep in mind. Conclusions, almost done. So conclusions: probabilistic forecasts are much more valuable than simple point forecasts of central tendency. You can assess quantal forecasts using the pinball laws. You can assess prediction intervals, central prediction intervals using the Winkler score. You can assess predictive densities using proper scoring rules. It's always good to keep in mind that your score is just one realization of a random variable, so it's always good. Let's bootstrap scores. Let's look at scores on different slices of the data. Is the picture consistent, or are we running into variability? Keep in mind that overfitting is still a thing. Even if our loss is something sophisticated, we can also overfit sophisticated things. And finally, keep in mind, nobody pays us for accuracy. They pay us for adding business value, and yet, of course, there's exceptions, and accuracy is often a good proxy for business value, but it's not the actual point. All right, thank you very much. Here's a book that I can very much recommend. Yes, I'm sorry, I was one of the co-authors here. It's also freely online. I didn't even put the link here. If you Google for it, then you'll find our Netlify URL, and you'll be able to read all of this on your own. Actually, we go into all of these evaluation methods, and yeah, thank you very much.